Why do we only ever see one side of the moon? If you've ever gazed up at the night sky, you might have noticed something peculiar about the moon. It always looks the same. No matter where or when you observe it, you only ever see one side, leaving the far side shrouded in mystery for millennia. This fascinating phenomenon, known as synchronous rotation, is a cornerstone of astronomy and offers a deep dive into the mechanics of celestial motion. Let's unravel the science behind this cosmic lockstep and explore why the moon has one face perpetually turned toward Earth. The key to understanding why we only see one side of the moon lies in the relationship between its rotation and its orbit. Like Earth, the moon rotates on its axis. However, its rotation period is precisely synchronized with its orbital period, the time it takes to complete one full orbit around Earth. Both of these take about 27.3 days, meaning that as the moon rotates, it also moves in its orbit in such a way that the same hemisphere always faces Earth. This perfect alignment isn't a coincidence but the result of billions of years of gravitational interaction between the Earth and Moon. To grasp how this happened, we need to dive into a concept called tidal locking. Early in the Moon's history, shortly after it formed about 4.5 billion years ago, it rotated much faster. However, Earth's gravitational pull created tidal forces on the Moon, causing slight bulges to form. Over time, these bulges acted like brakes, gradually slowing the Moon's rotation. Through a process known as tidal dissipation, the Moon's rotation synchronized with its orbit, achieving the stable configuration we see today. Essentially, the Earth's gravitational tug ensured that the Moon reached a state where one side always faces us. This leads to another fascinating question: what's on the far side of the Moon? While it's often called the dark side, this term is misleading. Both sides of the Moon experience day and night as it rotates and orbits the Earth. The far side remained hidden from human eyes until 1959, when the Soviet spacecraft Luna 3 captured the first images of it. Unlike the near side, the far side is heavily cratered and lacks the large, dark plains called maria, which dominate the near side. These maria formed from ancient volcanic activity, and their absence on the far side is still a subject of scientific study, potentially linked to differences in crust thickness between the two hemispheres. The Moon's synchronous rotation is also why lunar phases occur. As the Moon orbits Earth, the Sun illuminates different portions of it, creating phases like the new moon, first quarter, full moon, and last quarter. But because the Moon's rotation matches its orbit, the same features like the Sea of Tranquility or the Tycho crater are always visible to us, while the far side remains hidden from casual observation. Interestingly, the Earth-Moon system isn't unique in this respect. Tidal locking is a common phenomenon in our solar system. Many moons of other planets, such as Jupiter's Ganymede and Saturn's Titan, are also tidally locked to their parent planets. This gives astronomers a broader context for understanding how gravitational interactions shape celestial bodies over time. For students of astronomy, studying tidal locking provides key insights into orbital mechanics and the long-term evolution of planetary systems. The Moon's synchronous rotation also has cultural and scientific significance. Ancient civilizations, unaware of the science behind it, created myths and legends about the Moon's unchanging face. Modern scientists, however, use this stability to their advantage. The predictable nature of the Moon's motion makes it an ideal reference point for navigation and a prime target for space exploration. Missions like NASA's Apollo program and China's Change missions have studied both the near and far sides of the Moon, revealing valuable data about its history and composition. One fun way to understand this phenomenon is to model it yourself. Imagine holding a ball representing the Moon and walking around a central object representing Earth while keeping the same side of the ball facing the center. You'll notice that the ball needs to rotate once on its axis to maintain this alignment, mimicking the Moon's behavior. This hands-on approach helps illustrate the concept of synchronous rotation and the intricate dance between the Moon and Earth. In summary, the reason we only ever see one side of the Moon is a testament to the power of gravity and time. Through tidal locking, the Moon's rotation and orbit became synchronized, creating the stable, familiar view we see today. This phenomenon is not only a key principle in astronomy but also a reminder of the dynamic and interconnected nature of our solar system. For young astronomy enthusiasts, understanding the Moon's unchanging face is a gateway to exploring the forces that shape celestial bodies and their movements. So next time you look up at the Moon, remember it's not just a cosmic coincidence. It's a scientific masterpiece billions of years in the making.